the ones I want you to work on today and that we'll go through together, okay, are going to be 3, C, and D, because those are exactly exam level type of problems, right? And I'd like you to do, so 3C and D. Sorry, I gotta take those because they don't roll with it. So 3C and D. 6. Nine, 10, and 11 for now. Now, 9, 10, and 11 are boat questions. Okay, and we briefly talked about those the other day. So the idea here is that you're going to try something a little bit new. In fact, let's say do 9, 10, and 11 first. Then go back and do 6 and 3, C, and D. Okay, let's start with 9, 10, and 11. Alright, so try those ones first. And there, you can call them up on your phone because they're in the document there for Unit 1, the Unit 1 worksheet booklet. Because I do want to go over some more boat questions with you. Looking at today's quiz, it looks like we kind of get this whole vector component addition thing, which is good. I'm just going to practice it a bit more, but also introduce some of the different types of questions that can come up. Okay. Okay, so let's have a look at number 9. Now, if you recall, the other day when we talked about boat questions, I said there were 2 kinds. Rowing across, going across. Which one is this? Going across. Okay, because it says a boat that can travel on still water wants to travel north perpendicular to the current. Okay, so the boat's resultant is to be perpendicular to the current. That means that the boat's result is straight across the river. That's a going across. Okay, if it was rowing across, it would end up angled downstream. Okay, in this case, we want the resultant to be straight across the river. So this is a going across question. And the weird thing about a going across the river question is that the resultant is not the hypotenuse. It's basically the only time where that can happen. Okay, so what we have are the rowing speed of the boat. Okay, so it says on still water it can go 3 meters per second. That means you can row 3 meters per second. Okay. Since you're rowing into the current works against you a little bit. I had to draw that long enough. Okay, and the current is 1.2 meters per second. So there's this vector, my rowing, and this vector, the current, and they produce this. Okay, everybody with me there? So I end up going straight across. So this is my resultant velocity, not my resultant displacement. All the question wants to know is, what is the heading? In other words, what angle are you rowing at from perpendicular to end up going perpendicular? Follow what the question's asking for and kind of the strange wording. So I know the hypotenuse and I know the opposite side. What trig function am I going to use to get theta? Sine. Yeah, I don't even have to find out how fast I end up going across. The question doesn't ask that. It just wants to know what's the angle. Okay, so sine to the minus 1 of the opposite side, 1.2, over the hypotenuse, 3. And that should give me 24 degrees west of the north. Okay, for my heading. So a question like that, there's one mathematical operation to solve it. But it seems like a tough question because of its wording. Okay? And that's the challenge on a lot of vector questions, and quite frankly, on a lot of physics questions, is getting past the wording of the question. I hate to say it, but it's kind of like reading comp. Okay? I don't know, like, we did a couple of reading comp exercises in our CLCs one time, and us science guys, well, quite frankly, we really sucked at it. So we're like reading this, and we're like, I think it means this. Well, it means this. But I feel like it means this, and my feelings, they matter. And they're like, no, they don't. I'm like, oh, hurtful. Okay? But yeah, I guess there is like a right and wrong when you read something. And okay, there's a right and a wrong in physics when you read a question too. So we have to really kind of piece together the situation. All right, let's have you guys continue on with number 10. Okay, number 10 is very similar. Okay? It's a going across question because it travels directly north across the river. Okay, so this is a going across, not a rowing across question. All right, so very much like the last one, okay, we got a boat that travels directly north across the river. So here's the river, okay, at a velocity of 1 meter per second. So they're telling us the result. They're saying this line is 1.0 meters per second. And they're saying the river flows at a velocity of 0.5 meters per second east. Okay. In what direction is the boat headed? So that means that our rowing vector looks like that. We're not going to need to know the length because they don't ask for that. They just want to know that. Okay? And so sometimes a boat question that's going across actually gives you, here's your resultant. Instead of the last one, which gave us the hypotenuse on the opposite side, this one is giving us the adjacent and opposite sides. Right? So still similar idea, it's just now theta will be tan to the minus 1 of the opposite side, okay, over the adjacent side. All right, now just in case there's still some people that are like struggling with the whole Sohcahtoa thing, okay, remember how this works, okay? Sohcahtoa. Okay, when we're using these simple trigonometric ratios, okay, what we're being told here is that the sine of theta equals the opposite side divided by the hypotenuse. All right. So when we're looking at a triangle, a right angle triangle in particular, all right, here's my angle, here's theta. Okay, this is my opposite side. This is my adjacent side, and this is my hypotenuse. All right, so it's related to the angle. If it's beside the angle, so the arc is touching that side, that's the adjacent side. If the arc is not touching that side is opposite. All right, so if I want to find, in this case, theta, using sine, I would need the opposite side and the hypotenuse. Okay, if I'm using cos, the cos of theta is the adjacent side divided by the hypotenuse, so that would mean I need to know this side and that side. Okay? And if I'm looking at using tan, I would need the opposite side and the adjacent side, which is what I'm doing on this one. Okay, here's theta, it's what I'm looking for. I have the opposite side, the side that's not touching the angle, that's not the longest side, and the side that is touching the angle, that's the adjacent side. So that's why I'm using this. All right, so tan to the minus 1 of 0.5 over 1. So the tan of 0.5, or inverse tan, sorry, of 0.5. All right, is 27 degrees. And this direction is west of north. So 27 degrees west of north. The other way. Like this? Okay, because this, I was told this is my resultant, the 1 meter per second, that's a good question. Okay, and I know that my resultant needs to connect the two vectors that produce it. So I know I drew it first, and then I drew it head to head, which probably looked really weird because I said tail to head every time, right? Okay, but what I had to do was remember that this was my resultant, and my resultant connects initial and final. So I drew it first, which I should have explained when I drew it, okay? But I drew it first, and then I said, okay, I'm going to draw the two vectors that produce this. And I did draw them tail to head, okay? But I had to work backwards to get them. So when a question says, here's the resultant, that's what you'll have to do. The resultant is not going to be tail to head. It's going to be one thing head, and the other thing tail to tail. Yeah? Sorry, that's confusing, and I didn't explain that when I drew it. Sorry, that's on me. All right. Everyone follow that now? Okay. So number 11, still a boat question, even though it's a plane. A plane's a boat that flies in the sky. So still a boat question. Okay, give that one a try. All right, so on this one here, okay, the pilot wants to fly west, so that is the resultant is west. So in the same way as the last question, they're telling us what our resultant is. Okay, now the plane has an airspeed of 95 meters per second, and there's a wind blowing north. So since this is my resultant, I have to put the wind here. Okay, so sorry, this was, so we don't know what the length of this line is. Okay, but we do know that this line is 25 meters per second. Okay, that's the wind speed. And then our air speed is 95 meters per second. All right, so if I'm going to end up going due west and I've got a north wind, I've got to fly southwest a little bit so that the wind will blow it back to north, or sorry, to blow it north. So I would end up going west. Okay, so I'm looking for this angle right here. Okay, and if I'm going to find that, I have the hypotenuse and the opposite side in this case. So I'm going to find theta by using sine to the minus 1 of the opposite side, 25, divided by the hypotenuse, 95. And that should give me 15 degrees south of west. So if I go second sine of 25 divided by 95, and 15 degrees south of west. All right. Any questions on that one? Okay, try this one. I know we didn't say 12, but this boat question is not going across. This is a rowing across question, okay? And it's very, very typical of a rowing across question. It has more to it, okay? I'm going to ask you to do more things with it. So give that one a try, and we'll go through that one together here in a couple minutes. So this is a rowing across question. So we have a river, which they tell us is 125 meters wide. Okay. They tell us that a boat can travel 4 meters per second on still water and heads directly north across the river. So they are telling us the rowing speed and direction straight across the river at 4 meters per second. Now that means that boat is not going to go straight across the river because the river is going to push it this way at 2.1 meters per second east or directly downstream. So that means that the boat's resultant is going to look like this. In other words, if I had a drone flying over top of this, what it would see is the green line. It would see a boat moving diagonally across the river, even though that is the product of, or the sum of actually, a person rowing at 4 meters per second and a river flowing at 2.1 meters per second. So the green line is our resultant velocity. Okay? So it says, what is the velocity of the boat with respect to the shore? Is this angle measured from the shore? It is not. That angle is with respect to the shore. Now, how easy is it for me to get that if I find this angle? Super easy. It's the complementary angle. All I have to do is go 90 minus this angle. Or I could just redraw the triangle, put 2.1 on the bottom and 4 on the side. It doesn't matter which way you do it. As long as if a question says specifically, we want the angle measured from here, that you give the angle measured from there. Okay? It's easy to miss on a question like this. Okay, so I want to find my resultant velocity. I can find my resultant velocity with Pythagorean theorem. 2.1 squared plus 4 squared, okay, is going to give me the 4.5 meters per second. Okay, and then with respect to the shore, actually, I didn't even put the answer right on here. I have 28 degrees east of north. That is this angle. Okay, and that's not with respect to the shore. This one is with respect to the shore. Okay, so theta, as it appears in this triangle, will be tan to the minus 1 of 2.1 over 4. Okay, that'll give me my 28 degrees east of north, but that's not the angle they ask for. They ask for this angle, which is going to be 62 degrees north of east. Now, on a test, would I accept both for that question? I would not. Okay, on a vector addition question, vector components, where you're doing all that, and it doesn't say specifically measured from due east or measured from here, you can give me either one. But because this question specifically asks for it measured from a certain vector, you have to give that particular way. Okay, so that's all for part A. All of that is totally useless for parts B and C. I won't use any of that. Okay, any of the green stuff, none of that is going to help me with parts B and C, because they all refer to downstream and across. Okay, this is neither one of those. It is neither downstream nor across, it is both. Okay, or neither, whichever way you want to look at it. I can't use it, okay, because it doesn't point downstream and it doesn't point across the stream. So, if I want to figure out how long it'll take the boat to reach the opposite shore, I'm looking for time. I have the distance and I have the speed at which, or velocity, at which the boat is moving. It's going to move 125 meters at 4 meters per second. That means it's going to take 31 seconds for it to get across the river. Okay? That doesn't seem right. It's 125 over 4. That's not right, is it? It is? 5 by 4 is 31? Okay. Didn't seem right. Okay, 31 seconds. So now I know how long the boat is in the water. The whole time it's going across, what is it also doing? Going downstream. Okay, so do I know how fast it's going downstream? 2.1, right? So if they want me to figure out the distance downstream, the distance downstream is the velocity downstream, my blue line, times time, which is 31 seconds. Okay, this is the only thing that this side and this side have in common. How long the person's in the water for. Because once they get to the other shore, they're not going across or down anymore. Okay, so 2.1 times 31 is going to give me my 66 meters downstream. I cannot remember a time where I did not have a question like that on the unit exam.
Can you go over why you used the 4.0 meters per second and not the 4.5?
Because the 4.5 doesn't point in the direction that this is measured. This is a vector quantity, 125 meters directly across. Because this is not directly across, I can't use it with something that is directly across. You follow me there? It would be like saying you're traveling like southwest at 10 meters per second. How far north will you go? Like, I don't know. I'm not going north. I can't use that vector to find north. That's really a bad example. If I wanted to use v equals d over t with this number, I would need to know how far it is that way. Okay? I can only use vector quantities that have the same vector together in a v equals d over t calculation. Because they have to share a vector or they don't speak the same language. I'd be dividing apples by oranges.
But when we're talking about the path that the boat takes going across, it's taking the green path, right?
It ends up doing the green path because it's also doing the black and the blue. Maybe try this, Dave. Is it further straight across or along the green line?
Along the green line.
Right. So I can't use the green line with this because this vector doesn't go this way. It's longer. I might be going faster, but I also have to go further, which would mean I'd get the same amount of time. Right? If I figured out how far it is to go this way, which I could, I would be using the 31 seconds. Right? All three of these take 31 seconds. to get to the other side. But because this one's longer than 125, it also has to be faster than 4. I feel like I'm talking myself in circles here, but maybe did that make more sense? Or
Yes.
yes and no? Or are you just placating me because you want me to stop confusing you? Okay, so the big thing here, the rule to remember, whether you kind of understand the rule or not, is that if I want to do a calculation with vector quantities other than adding them together, they have to share the vector. Okay? Displacement and velocity always have the same vector, right? When we talked about that trip to Walmart, when we first started talking about vector quantities and scalar quantities, the displacement and the velocity both have the same vector. Okay? They have to. So that means I can't take a vector quantity like this one and use it with a vector quantity that doesn't point the same vector. Yeah? Because they're talking about the same trip from different points of view. And those points of view don't go together. Yeah? All right, we'll call it a day there. We'll do a little bit more vector stuff tomorrow and then kind of see where we're at. All right, guys, if you're struggling with this, come in and see me for some help. Okay?